Hey up everybody, how do? Welcome to this video where we're going to take a look at another interesting problem from mathematics, and we're going to take a detailed look at the problem solving process and how that looks when it comes to approaching non-routine problems in mathematics. For this video I've chosen a problem from the mathematics admissions test from 2016, or the MAT. So those of you who are maybe applying to university here in the UK to do mathematics or computer science or something like that may be aware of the fact that you might have to sit an extra exam. It's usually takes place in about November of each year, so you may have to sit the MAT exam as part of your university admissions process. MAT exams are chock full of non-routine problems in mathematics. So you've got to really think on you've got to be on your toes. You've got to really know your stuff. The solutions to the problems are very non-routine. You've really got to understand the A-level maths that you learn on a kind of deeper level, really, to be successful in an MAT exam. So we're going to be taking a look at one of the problems from one of the MAT tests. It's question number 5 from the 2016 paper, and in this video what I'm going to be doing is I'm not just going to be giving you a model answer or model solution to the problem. I'm really going to be kind of walking you through the problem solving process as it happened for me. So I found a solution to this problem. The solution that I give you is my solution. It's not the solution that I've just taken from the mark scheme or something like that. This is my solution, and the whole point is that I articulate as clearly as possible what kind of things were going on as I was trying to solve this problem. What kind of things were I thinking about? What caught my attention? What kind of things did I try that maybe didn't work? So it's going to take a while to get through this video. Don't just expect that I'm just going to say, do this, do this, do this, do this, do that, and you get the answer. It's going to be, there is going to be a bit of to-in and fro-in, maybe going off on a bit of a tangent, no pun intended, here and there, and showing that even though something might have been a good idea and it might have been worth trying, it actually didn't take us in the right direction, and things like this. So it's going to be a little bit messy, and that's deliberate because the problem solving process is messy, and I don't want to give the impression that the problem solving process is always nice and straightforward and that you should expect to see solutions to non-routine problems like that, because it just doesn't happen like that. I really want to capture that messiness of the problem solving process. So my background, just so that you know, my background is in mathematics, and particularly in one-to-one mathematics tuition, where I've got a lot of experience at helping people prepare for MAT tests, prepare for their university admissions, prepare for step exams, as well as preparing for their normal A-level maths and further maths exams, and even GCSE and IGCSE as well, particularly the higher level. So let's get on with the problem. Let's have a look at what the problem is, and let's see how we might go about solving it. So there's a couple of parts to this problem that are fairly straightforward, and then there's a couple of parts that are really not so straightforward. Be prepared when it comes to an MAT to think. Be prepared to take the time to think. Don't expect that a solution is going to come to you straight away. It's very important that you articulate your ideas, even if the idea that you have turns out to be wrong. It's very important that you show your examiner what your ideas are. What your examiners are going to be looking for on an MAT test is potential. Do you have the potential to go on to do mathematics at university level and be successful? So it doesn't all come down to necessarily did you get a full solution to the problem. It's really, can you show that you have good ideas? that you can articulate those ideas, that you can follow through on those ideas, and you can make an attempt at solving the problem. Okay, so let's have a look. So the information that we're given is that this question concerns the sum Sn, which is defined to be 2 plus 8 plus 24 plus ... plus n times 2 to the power of n. Okay, if it does appear that I'm looking down here, by the way, that's because I am, because I've got it on the computer screen here, the details of the problem. I've also got a few notes here because it is quite a lengthy problem, so I might refer to my my own notes from time to time just to remind me what kind of things I was thinking about. Okay, so the first part of the problem is let Fn be equal to an plus b times 2 to the power of n plus c. For constants a, b, and c yet to be determined. And suppose that Sn is equal to Fn for n greater than or equal to 1. For all n greater than or equal to 1, sorry. By setting n equals 1, 2, and 3, find 3 equations that must be satisfied by a, b, and c. So in this first part, it's a very gentle introduction to the problem. You're actually being told what to do. That's not going to last, by the way. At some point, you have to take over and do the thinking for yourself. So let's have a look anyway. So when n equals 1, we get that f of 1 is equal to S1, but F1 is equal to a times 1, so it's a plus b times 2 plus c. And this must be equal to S1 is equal to 2. Okay, so that gives me my first equation, and I'll just outline that. Where's my red pen? This red pen. Just outline that equation. Outline it from there. Okay, let's get rid of that bit. Okay. So then we're told that to choose n equals 2, and we know that f of 2 is equal to S2, and F2 is equal to, so it's going to be 2 to the power of 2, which is 4, times 2a plus b plus c equals, and S2 is going to be 2 plus 8, which is 10. So that gives us another equation. And then finally, when n equals 3, f of 3 is equal to S3. F of 3 is equal to 2 to the power of 3, 8 times 3a plus b plus c equals 2 plus 8 plus 24 is 34. And that gives us our 3 equations. So if you're comfortable with simultaneous equations, this should be fairly straightforward. We can simplify them up a little bit. So equation number 1, call this equation 1, equation 2, equation 3. Equation number 1 we can write as 2a plus 2b plus c equals 2. Equation number 2 is going to be 8a plus 4b plus c equals 10. And equation number 3, 24a plus 8b plus c equals 34. Okay, hopefully I've not made any mistakes there. Right, so this is just a fairly straightforward simultaneous equations problem. If you really want to, you could set it up as a matrix problem. I don't really think that you need to, but you can do that if you want to. So what I did was effectively equation 3 plus 4 times equation 1 minus 4 times equation 2. And this gave c is equal to 2. So plug that into maybe go back to these two equations then, and what you end up with are the two linear simultaneous equations in two unknowns, namely a plus b is equal to 0. So replace the c with 2, subtract 2 from each side, divide through by 2, and for this one, this will cancel down to 2a plus b equals 2. So this implies that a is going to be equal to 2, b is going to be equal to minus 2. Nice and easy. Okay. Actually, we've done the first two parts of the problem here, because the second part of this problem, problem number 5, was solve the equations from part 1 to obtain values a, b, and c. Once I'd got the equations, it was almost automatic for me to go ahead and solve them. I didn't even bother to read the second part of the problem, to be honest with you. It's kind of obvious that you're going to have to solve them, I guess. Okay, by the way, guys, this is a fairly new YouTube channel. At the time of making this video, I've only got a few subscribers. It'd be really great if you would hit the like button and also subscribe to this channel. I'd be really grateful. And also feel free to let anybody else know, that any of your friends that you think might find this channel useful. Encourage them to watch these videos and subscribe as well. That'd be great. Cheers. Okay, so that's the first two parts of this done, and that's fairly routine. So this is the calm before the storm. Okay, so now we know that Fn can be written as, and we're going to have to bear this in mind because we're going to be using this quite often. It can be written as 2n minus 2 times 2 to the power of n plus 2. So there's a lot of 2's flying around here, by the way. Okay, so moving on to the third part then. So we can get rid of all of this. We're done with all of this. By the way, I'll leave a link in the description to this video to this MAT past paper, so you can see the problem for yourself. Okay, so the next part of the problem, it says, using these values, the values of a, b, and c, that is, show that if sk equals fk, so this is if sk equals fk, for some k greater than or equal to 1, then sk plus 1, this implies then that sk plus 1 is equal to fk plus 1. So those of you that are maybe familiar with proof by induction will see this is effectively a proof by induction that we're going for here. Although the term proof by induction is not actually used here, it's effectively a proof by induction. Okay, time for a coffee. And of course, this is my Maths Made Easy mug. Okay, so notice that all we've done so far is found values of a, b, and c that guarantee that f1, f2, and f3 are going to be equal to s1, s2, and s3 respectively. Finding those values of a, b, and c that in itself does not guarantee that fk is going to be equal to sk for all values of k. Okay, but this will. So the way that proof by induction works, for those of you that don't know, is the logic behind it is that you've got a series of propositions corresponding one to each positive integer. So you've maybe got P1, proposition which applies to, so it's a proposition that involves the integer 1, and then you've got P2, and then you've got Pn or Pk. So what you do is you show that P1, this proposition, is true, which we've shown here in the sense of showing that F1 is equal to S1. This might be our proposition. We've shown that this is true because we can show that this is equal to the value of S1. And if you can show then that Pk, the proposition Pk, which in our case is going to be f of k equals s of k, that if that is true, and this implies that and this implies that Pk plus 1 is true, then what you can say is that Pn is true for all values of n. So I've not necessarily explained this fully in any way, shape or form. It's just a quick idea of what proof by induction kind of looks like if you're not familiar with it. What I would recommend is that if after this video you're still not really sure what proof by induction is, which is highly likely, based on my explanation there, there's plenty of resources that you can refer to. But if you are in any difficulty, if you want some clarification, feel free to leave a comment. Feel free to ask in the comments section for some clarification about how proof by induction works. It's just I don't want to drag this video out too much with proof by induction. I really want to get on with the problem at hand. Okay, so what we do then is we start with, since we know that fk is equal to sk, we also know that sk plus 1 is equal to sk plus k plus 1 times 2 to the power of k plus 1. So why is this? It's because we've effectively got some sort of relationship between the consecutive terms of this sequence. So these Sn, they form a sequence. S1 is equal to 2. S2 is equal to 2 plus 8. S3 is equal to 2 plus 8 plus 24. So notice that, for example, S2 is equal to S1 plus 8. S3 is equal to S2 plus 24. And this is where I'm getting this relationship from here. Okay, so if we're interested in sk plus 1, then the first k terms of this sum are just sk. So then adding on that final term to sk will give me sk plus 1. So that's where this relationship is coming from, if it's not obvious. Okay, so this is equal to then f of k, because by assumption s of k is equal to f of k. But we know that f of k is equal to 2k minus 2 times 2 to the power of k plus 2 plus k plus 1 times 2 to the power of k plus 1. Okay, and then it's just a bit of an algebra juggle. So I can take 2 out as a common factor here. And I get 2 to the power of k plus 1 times k minus 1 plus k plus 1. I'm not going to go through all of the details of every single step that I take, by the way. Some of the steps of the algebraic manipulation that I'm going to be taking, I'm going to take it for granted that you kind of understand. But again, if you do need some clarification, ask in the comments section, okay? So this is going to be equal to 2 to the power of k plus 1 times k minus 1 plus k plus 1 is 2k plus 2. This pen's getting a bit naff. Let's try a new pen. Which is equal to, okay, I need to fiddle this in here a little bit. And this is a common thing to do in mathematics. It sounds like a silly thing to do, but to add 0 to something, but in a very particular way. Okay, this can be really effective sometimes, in the same way that multiplying something by 1 in a very particular way can be used to great effect in some cases. So, for example, when you find equivalent fractions, for example, so you start with something like 3/5. You know that if you multiply numerator and denominator of this by 3, you'll get 9/15, I hope, which is equivalent to the first fraction. What have you done there? Well, you can interpret it as multiplying by 1. You multiplied numerator and denominator by 3. That's the same idea as multiplying by the fraction 3/3, but 3/3 is just equal to 1. So it's sometimes, if I just said, oh yeah, you just add 0, this is not fully descriptive of what I'm really doing. It's adding 0 in a very particular way. So I'll show you what I mean. So we've got 2k plus 2 minus 2. So I've added 0. I've added 2 and then I've subtracted 2 straight off. Why do I do that? Because then I can write 2k plus 1 minus 2 times 2 to the power of k plus 1 plus 2. And this is f a k plus 1. Okay, so in other words, we've proved that under the assumption that sk is equal to fk, which is what I've replaced the sk with here. This is fk. What I can show is that sk plus 1 is equal to fk plus 1. Okay, so this is the induction step. This is the inductive step that we've just proved here. So what that would allow us to say then, effectively, is that Sn is equal to Fn for all n greater than or equal to 1, where n is an integer. Okay, so that's the third part of this problem done. Nice and easy so far. Now we come on to something that's a little bit trickier. So let's have a look. I'm going to refer to my notes. So I did, this took me a couple of attempts to get this. Really, the difficulty was just getting the algebra right. Sometimes the algebra can be very fiddly in problems, and a little slip in your algebra somewhere can really just throw things off, and that's what happened here for me with this part. So I kind of had the right idea, but I just kept mucking up on the algebra. Didn't help that it was late at night. Okay, so find simplified expressions for the following sums. So we've got Tn, which is equal to n plus, 2 n minus 1 plus 4 n minus 2 plus 2 to the power of n minus 1 times 1. Okay, so this is a new sum that we've got here, and it's at this point where it would be very normal to start thinking, what's this got to do with what we've just been doing? Okay, and sometimes this question can only be answered by actually just plowing ahead and doing something. It wasn't clear to me at all how this, and there's another sum that we're going to have to deal with in a second, how this was related to what we'd already been doing, what we'd already figured out. Okay, in a way, you've just got to kind of trust that something's going to come out. If you've got to pay attention, you've got to really think about what you're doing. But if you're paying attention, hopefully at some point you will see the connections between what you're doing now and what you've already done. This is part of the problem solving process. There's nothing that you can do to get around this. You just have to accept this as part of the problem solving process. So one thing that I did with this, and I did this almost automatically, by the way, and I'm not saying that this is something that you should always do. It was just something that I felt was right to do. I replaced this 1 here with this expression, n minus n minus 1. Okay, because n minus 1 is equal to just 1. So I'm rewriting 1 in a very particular way. Again, it's that idea of doing something in a very particular way. That very particular way is wholly dependent on the problem, the specific problem that you're trying to solve. So I can't say always do that, because it wouldn't make sense in certain contexts. To do this would be nonsense to do it. Not wrong necessarily, but not helpful. Okay. What made me do this? Because I wanted this to much more clearly resemble the rest of the terms here. So I could even go so far as to say I was maybe even thinking about this as n minus 0. I actually wasn't, but you could go that far and say, well, think about this as n minus 0. And you could even stick a 1 in here as well, just so that one thing that really helps when it comes to dealing with expressions like this is where you've got a series of terms is if there's some clear visual similarity between all of the terms. I mean, the nature of each term is expressed, is already there. It's fully expressed in what we originally had. Oh, sorry, the 2 to the power of n minus 1 times 1, for example. Arguably, all of the information that we need is contained there. This is no different, really. This contains no extra information, strictly speaking, than this does. It's just it's kind of a visual thing. Okay, when all of the terms, there's something that's clearly the same that you can see at a glance. This sometimes makes things a little bit easier to deal with. At least it does for me. So maybe try it out. Maybe it's something that you could try out. If you've got terms that appear to be different in some respect, is there some way that you could bring some sort of visual unity to what you're working with? Okay, so the next thing I did was expand it out. Okay, so I get, again, n plus 2n minus 2 plus 4n minus 8 plus, plus 2 to the power of n minus 1 times n minus 2 to the power of n minus 1 times n minus 1. Okay, hopefully that's right. So then, what did I do? Well, I grouped these terms, and I'll underline them. These terms that have a factor of n, I grouped together. So I wrote this as n plus 2n plus 4n plus 2 to the power of n minus 1 times n minus, and notice that all of the rest of the terms, all of the remaining terms are going to be negative. It's going to be minus 2 plus 8 plus 2 n minus 1 times 2 to the power of n minus 1. Okay, now you might start to see the connection between what we're doing here and what we've just been doing, right? This is Sn minus 1 effectively, right? Good stuff. Okay, so what can I do here? Well, I can take n out as a common factor, so I get n times 1 plus 2 plus 4 plus up to 2 to the power of n minus 1. That's just the geometric series. That's going to be easy to deal with. Minus, and it's going to, this I recognize as being Sn minus 1. So this geometric series here, so the sum of the first n terms of a geometric series is a times r to the power of n minus 1 over r minus 1, where r is the common, a is the first term, which in this case is 1, r is the common ratio, which is 2, and n is the number of terms, so n is just equal to n. So we get n times a, which is 1, times r to the power of n, 2 to the power of n, minus 1, over, and it'll be r minus 1, which is just 1, minus Sn minus 1 is equal to Fn minus 1, minus 2 n minus 1 minus 2 times 2 to the power of n minus 1 minus 2. Okay? And now it's just tidy this up a little bit, tidy this expression up, and this is where I was making a right mess when I was originally going through it. It shouldn't have done. There's nothing particularly difficult about the algebra. It's just one of those things. Sometimes you just lose concentration. You just have a little slip, and everything just seems to go to go wrong from there on. So all I can say is really try to concentrate as much as you can on when you're doing your simplification with algebra. Okay, so we get 2 to the power of n times n minus n minus, okay, let's take it a little bit steady here. So 2n minus 2 times 2 to the power of n minus 1 minus 2 equals n times 2 to the power of n minus n minus, that's going to be, so twice, 2n times 2 to the power of n minus 1 is going to be n times 2 to the power of n, minus plus, so that's going to be minus 4 plus 4 times 2 to the power of n minus 1 minus 2. So cancel, that can be simplified to 2 to the power of n plus 1 minus n minus 2. Hopefully that agrees with what I had. I'm just going to check. 2 to the power of n. Yeah, that's it. Okay. And just because I did have a few mishaps with my algebra, just to be on the safe side, I did check this for the first few values of n, just to convince myself that it was likely to be correct. And it turns out that the values match up. So this expression, when n equals 1, does give the value of t1. When n equals 2, 3, and 4, also gives the correct values of t2, 3, and 4 respectively. So that's obviously not a guarantee in and of itself that this expression is going to work for all values of n, but it's a good sign. And after the few oopsies that I made with my algebraic manipulation, I was a bit relieved to see that happen, to be honest with you. So that's the expression that we've got for Tn. And I'm going to write that somewhere because that's going to be kind of useful to us. So Tn is equal to 2 to the power of n plus 1 minus n minus 2. Okay, so we're done with that part now. So we're on to the next sum. Now, which is un. So we're given that un is equal to half plus 2/4 plus 3/8 plus n over 2 to the power of n. Okay, so now I think the tendency here is to see the 2, 4, 8 up to 2 to the power of n here and kind of compare with, is that right? 2, 4, 8. Sorry, no, I'm getting a little bit ahead of myself. No, forget that. So it took me couple of minutes of thinking about what I wanted to do here, the first thing that I did was to write this as the following: 1 times 2 to the power of minus 1 plus 2 times 2 to the power of minus 2 plus 3 times 2 to the power of minus 3 plus n times 2 to the power of minus n. I couldn't really see, once I wrote this, I couldn't really see how this was going to be useful to me. As it is there, it is actually kind of what I need to do, and we'll see in a second how it's kind of relevant. But the point is that sometimes, even if you don't know how something's going to turn out, even if you think that you're going to do something and there's a chance that it's not going to work or whatever, sometimes it's worth actually just going ahead and doing it anyway, because it might actually stimulate another idea that does work. And that's what happened here. So I got to this stage, and when I saw this first, I thought this is not really useful to me. I was hoping to see something resembling this, or maybe resembling the TN. But after a couple of minutes of thinking, it occurred to me what I needed to do. Multiply through by 2 to the power of n. So you get 2 to the power of n times u sub n is equal to, and it's going to be 1 times 2 to the power of n minus 1 plus 2 times 2 to the power of n minus 2 plus 3 times 2 to the power of n minus 3, all the way up to plus n. I'm going to write it as times 2 to the power of 0. Okay. And then I had to think about another thing, something else that I needed to do, because once I got to this stage, again, I was kind of a little bit stuck. This is how it is sometimes. This is how it is. Sometimes you do something, it is what you need to do, but you've got to figure out how. And I had to figure out at this stage that I needed to do this, but even when I'd done this, I still had to figure out what I needed to do next. And it's an obvious thing, which I'll tell you after I've had my sip of coffee. Okay, so the next thing that I did was simply reverse the order of the terms. So I ended up with n times 1 plus, the next one is going to be n minus 1 times 2 to the power of 1, which is 2, plus, and then we get down to here, and we get something like n minus, and I'm going to write it, n minus 2, 2 to the power of n minus 2 plus n minus 1 times 2 to the power of n minus 1. Why is this useful? Because it turns out that this is Tn. So all of this here is equal to Tn. It matches up exactly with Tn. So in other words, Un is equal to Tn over 2 to the power of n. So all of these steps that I'm taking here are just, they're in many cases just motivated based on what I see in front of me at that time. Okay, so when I set about this, there wasn't a specific plan. This is not a routine sort of thing. There isn't a way of doing this, as far as I know. It's just being prepared to do something and using what you see in front of you to motivate further things to do. Now, initially, this might be quite difficult, and this is why it's really important to get plenty of practice at solving genuinely interesting and challenging problems before you get to the MAT. If you're if all you've done really is fairly routine things from your standard kind of A-level maths textbook, you might find the MAT a little bit of a challenge, because not because you don't have the techniques or the ability to solve the problems. It's just you might not be used to actually going through that problem solving process. So the whole point of these videos is to describe that problem solving process, which is messy, and there's no systematic way of going through. The only way that I can present the problem solving process accurately is to show you, to try to describe to you how it works, at least in my personal experience. Okay, so each of these steps is something that I've had to think of to do based on what I see, and really dig into my understanding, my knowledge, and my creativity to come up with a solution. I don't consider myself a terribly creative person, but that you do have to have a certain level of creativity to find ways to apply what you know in creative ways when it comes to solving problems. So we've got un equals tn over 2 to the power of n. In other words, un is going to be equal to 2 to the power of n plus 1 minus n minus 2 over 2 to the power of n, which is 2 to the power of, that's just 2, minus n times 2 to the power of minus n minus 2 times 2 to the power of minus n, which you can simplify to 2 minus n times 2 to the power of minus n minus 2 to the power of minus n, I want to get this right, minus n plus 1. Hope that's right. Tell me if I've made a mistake, by the way, but okay. That's, we found simplified expressions then for tn and un. And notice, by the way, that all we're told to do as part of this problem is to find simplified expressions for the following sums for tn and un. It doesn't give us a specific form to write, anything to aim for. So how do you know what your final answer is going to be? Well, that's something that you've got to use your own judgment on. This is arguably part of what you're going to be examined on, is what can you use your own judgment to determine what sensible simplified expressions are going to look like. Can you recognize them when you get there? So you've just got to use your own judgment to figure that out. Okay, so that's what we've got for un. Un is equal to 2 minus n times 2 to the power of minus n minus 2 to the power of minus n plus 1. Okay, so moving on. 1 minus, yeah, okay. So moving on. Final part now. And this was, for me, the most challenging part of this problem. Although that part that we've just been looking at, part 4, was quite challenging in itself. This took me a little bit more time to figure out. So now we need to evaluate, we're told, computer's gone off, find the sum from k equals 1 to n of sk. Okay, so this was, there were a few things that I tried with this, but one thing that I recognized, that one idea that I had more or less straight away with this, and it turned out not to be particularly useful, but again, better to have an idea, follow it through and see that it doesn't work than to not have an idea at all. Okay, so what I did was I wrote this as, it's going to be S1, equals S1 plus S2 plus S3 and so on and so forth. Well, S1 is equal to 2, plus S2 is equal to 2 plus 8. S3 is 2 plus 8 plus 24. And then we've got S4, And if we continue this, we get to Sn, which is going to be 2 plus 8 plus 24 plus, and eventually we get to n, 2 to the power of n. So what I noticed was that there's going to be n 2's that we add together. So n times 2. And then there's going to be n minus 1 8s. Then there's going to be n minus 2 24s. And there's going to be, right on the end, there's just going to be a single n times 2 to the power of n. This was my original idea, okay? So that this sum is going to be equal to this. And I expanded all of this out. So you get something like 2n plus 8n minus 8 plus 24n minus 48 plus plus n times 2 to the power of n. Collect these terms together that have the n as a factor, and you take out a common factor. There you get 2 plus 8 plus 24 plus up to 2 to the power of, oh, actually, I wrote this, how did I write that? Yeah, okay, again, I used that little trick of trying to get this to match up with these a bit more closely, because the n 2 to the power of n kind of corresponds to these parts. So I wrote here, instead of n times 2 to the power of n times 1, n times n minus 1, which means that I'd get an n squared 2 to the power of n plus n squared 2 to the power of n. No, I don't get that, do I? That's it, right. N times 2 to the power of n times n minus 1. Okay, so I collected all these terms together, so I got plus 2 plus n times 2 to the power of n. I was quite pleased when I saw that, because I thought, that's great, this is Sn. I know an expression for Sn. But then came the problem for me, because I've got minus 8 plus 48 plus, and then finally n times n minus 1, 2 to the power of n. So I tried to have a play around with this. That was easy to deal with, that bit, but then this here, I couldn't really figure out a way to deal with this, and it took me a good 5-10 minutes of playing around with this to come to the conclusion that that's probably not what I want to be doing. And stupidly, I kind of overlooked something that we'd already done. Okay, so through all of the calculations, finding expressions for Tn and Un, I kind of lost sight a little bit of something that we'd already done that was going to be really useful here. So, by the way, be prepared sometimes to give up on ideas. I was convinced initially that this was the right direction to be going in, based on the fact that I got this result here, this expression. I thought, this must be going somewhere, until I realized it's probably not going anywhere. Okay, at that point, you've just got to kind of give up and try something else. Okay, I know when you get into an exam, it's not the kind of thing that you want to hear, that's what you're going to have to do, but that's the truth. So let's have a look. By the way, don't forget to hit that subscribe button, give this video a like, it'd be really appreciated. So sk from k equals 1 to n, well, this is equal to, I've smudged it a little bit there, the sum of, well, fk from k equals 1 to n. So in other words, 2k minus 2, 2 to the power of k plus 2. This is what I need to be working with. Okay, so expand this out using the linearity properties of summations. Then we get 2k times 2 to the power of k minus 2 to the power of k plus 1 plus 2, which is equal to twice the sum from k equals 1 to n of k times 2 to the power of k minus the sum from k equals 1 to n of 2 to the power of k plus 1 plus, and this is just going to be 2 times n. So for those of you who are paying attention, you will see that this is just Sn. So we get twice Sn. Remember, Sn is equal to Fn. Bingo. So we get 2n minus 2, 2 to the power of n plus 2, minus, this is just a geometric progression. The first term, a is going to be equal to 4. The common ratio is 2. The number of terms is n. So the sum of this is just going to be 4 times r to the power of n, 2 to the power of n minus 1 over r minus 1, which is 2, which is 1, sorry, minus 4 times 2 to the power of n minus 1 plus 2n. And this all simplifies to 2 to the power of n plus 2, n minus 2, plus 8 plus 2n. Is that right? Yeah, plus 2n plus 8. Okay, and that's the sum of SK. So I've left out some of the details in here about how I've got from here to here, but it's just really expand out, use laws of indices, things like that. Nothing particularly difficult, especially if you're looking to do an MAT. Really, you should be able to figure out what I've done in there. Okay, so that brings us to the end of this problem. If there's anything that you don't understand, if there's anything that you want clarification on, please leave a comment in the comments section. If there's anything, by the way, that you would like to see me cover in a video relating to problem solving, let me know as well in the comments section. So that brings us to the end of this particular problem. I'm going to be uploading more videos over the coming weeks and months relating to 6th term examination papers and MAT. So make sure you keep checking back on this channel. Don't forget to hit the subscribe button. That brings us to the end of this problem and the end of this video. Cheers, guys.